Now we come on to a few of the very many important possibilities here. The first one we have is a rather general discussion of cloud computing for the financial industries, which is banking, security and investment, insurance. And obviously, that says here the discussion is only within the US, but of course, it could be the ideas are basically global. And the suggestion is that big data technologies can be extended into the financial industries to advantage. And examples of important analytics, which actually use MapReduce, which is Hadoop is an example of fraud detection, risk analysis, and also for overall what you might call knowledge management and providing rich sources of information for customers and, of course, your in-house uh, security analysts. Um, a lot of this data is currently done by relational database management systems, Oracle, MySQL, etc., because this is a relatively old application, and so some good applications were already developed on the older technologies. And also, there are many aspects of banking, like uh, processing your credit card application, for which relational database management systems are perfect. For individual so-called transaction processing, OLTP, online transaction processing, I don't think big data has got necessarily any better solution than the older technologies, which are highly optimized for that particular example. In fact, the reason why big data and the newer technology are becoming important is because traditional databases were tended to have a huge emphasis on transaction processing with relatively simple atomic transactions, whereas today's big data applications tend to, even if they have streaming transactions, tend to be much more complicated transformations and filtering is needed on the data. And much more complicated ways of integrating the data together are needed, for which the traditional databases can be used, but are not clearly the most effective solution. So this has this streaming characteristic, which I already mentioned actually earlier in the government use case section. Um, and we know that a lot of, in fact, possibly most banking data comes in a streaming fashion. The stock market keeps ticking away, and obviously has transactions that come every second, and perhaps even faster than that if you really want to have your analytic engine poised to take advantage of small market imbalances. So streaming is a very important example here. And that we will see that in a lot of other cases with sensors, with just people actually coming in from the web. All of those type of applications tend to be streaming because they have a sort of big repository of data and they have other related data coming in, adding to the original data. And this is very important. It requires special processing. And if you're doing, say, recording things in clusters, um, you have to run a pretty sophisticated algorithm to find your initial clusters, and it uses a large data set. However, once you have those clusters and along comes a new point, you can take that point and see which cluster it belongs to without redoing the cluster analysis. So there are aspects of streaming processing which are special and should be done specially. Here we have an interesting contribution from Mendeley. Many of you may know Mendeley. It's a startup which is basically doing citation management and analysis. And as you see, it has a big database, currently 15 terabytes, but growing rapidly. And that has all the types of things we want to cite, which for scientists are research documents. And they have technologies to allow one to group these things together, to create shared bibliographies, and use the activity recorded on Mendeley to actually find out real results on what's important scientifically. There are actually many such, there's ResearchGate and academia.org .edu, which are also similar types of companies. Um, so they use text mining and classification systems, which automatically recommend what research might be useful to you. Because when you have all the world's data and you see what somebody is currently researching, you can suggest other things. That's the same idea that Amazon uses with books and other things. When it sees what you've read and what then looks at this database to see what people who read similar things that you have also read, they suggest that to you. So that's the so-called recommender engine, a key technology we will cover later in this course. So they note that Mendeley is actually supported on a commercial cloud, Amazon Web Services, and they're using they use Python as a language, but the other aspects are technologies from the Apache Big Data Stack. And they have their own, they don't explicitly say which machine learning library they use. They use latent Dirichlet allocation, which we will not cover particularly in this course, but it's an important technique for analyzing documents and dividing those documents into groups based on so-called latent or hidden factors, and this gives you a way of generating topics and things like that. And as they point out that they're currently doing everything in batch with MapReduce Hadoop. They have 400 million documents, and they have about 700K new uploads every day. So managing all of this is complicated, and that's what they're using all these technologies to do. And I expect this type of application to grow in importance. I think the traditional approach to managing documents, which is rather isolated, this clearly throws away an enormous amount of information. For instance, I edit a journal. I believe these technologies could make my editing of journals so much easier because I should be able to go to a properly curated set of data like that in Mendeley and find out all the best reviewers for a new submitted article, because the Mendeley can take one article and find out all the closely related articles. So we introduce here for the first time some very important new computational types. MapReduce itself, we did MapReduce Stat. The general MapReduce has more complex reduction functionality, and it is the most important big data processing paradigm. We will cover MapReduce later on. Iterative MapReduce is something which is of growing importance because it's when you want to look at certain applications involving iteration. Collaborative filtering is not really iterative, but clustering is. And latent Dirichlet allocation is iterative. And then an iterative MapReduce, which stores information, caches information in memory, is an appropriate approach. Classification is a very broad term, and so many of these big data problems want to take their data and divide it into categories. And finally, under parallelization, we have item parallelization. And here the items are basically documents, the things that are being cited. And we will find later on some related examples, tweets, blogs, documents, and web pages. And one looks at the so-called bag of words model typically, and looks at the character of words in these documents, web pages, tweets, and blogs. And it's those characters and words effectively characterize a document. You look and see what types of words it had in it, how often they occur, and compare that with other documents. And that allows you to effectively match documents. So this is a powerful technique that we will discuss later on in the class. Well, here is actually a survey summary in which Mendeley was done by Mendeley. This Netflix analysis was done by me, and so I apologize to Netflix if I messed up. I did actually read tutorials about Netflix on the web. And what is the purpose of Netflix? Well, if you're a user of Netflix, the purpose of Netflix is to deliver you your favorite movie. If you're Netflix, your purpose is to make the most money satisfying your users' needs. And so actually, this particular use case points out that the actual objective function for a commercial provider of a cloud service is a little complicated because it is not just user satisfaction. Making one user satisfied is when you may be able to make your one user incredibly happy, but what you need to do is to make lots of users happy, and that may not be quite the same problem. And so you need to, for each user, you're in fact that user is probably a household with multiple points of view and interests, and you need to maximize the consumption of movies by that household, and also make certain those movies were good movies so that that household wants to keep their Netflix subscription. So you need to choose the right videos to present to them as possible things to stream down. We have, of course, the need to do what things that YouTube does, store movies in the cloud, download it, have metadata attached to them. The users have profiles which are used for doing this matching, and the users are very critical data is the ranking of movies by users. That's what's used in probably the most powerful collaborative filtering algorithms. Netflix, like a lot of these companies, is a very complex, sophisticated analysis system. If you read the literature, you will find elegant, simple discussion of systems, but that's not what these people do. They use something very complicated because they've actually able to do that, and that's what they need to do to make the best possible service. And these algorithms they use are continuously changing, and they're able to. When Netflix has enough customers, they can afford to use a subset of them, a small subset, to test a new idea. And so actually that may lead to an improved performance or actually maybe a poorer performance for that subset. So no algorithms are deployed broadly without being tested first on a subset of the audience. And the current approach is, as I essentially built around recommender systems and the streaming video. And those recommender systems are always personalized. They use all sorts of sophisticated technologies, clustering, LDA, latent Dirichlet allocation, elastic nets, just ordinary regression, and all these fancy machine language things, gradient boosted statistics, gradient boosted decision trees. There was a well-known competition which Netflix held to improve its ratings by the accuracy of the ratings by 10%. And the winner of that actually combined 100 different algorithms for the final answer. They use a SQL, traditional databases, NoSQL. They use MapReduce, and all their stuff is hosted on Amazon Web Services. And as I say, the Netflix is typical in some ways or aspects of Amazon. It's e-commerce part of Amazon. The streaming video is common with things like iTunes, Google Play, Pandora, YouTube, Last.fm, etc. This is a really competitive business, cutthroat. Netflix has to stay ahead, and they have to track what other people do and what the trends are, and they have to look at new business initiatives such as building their own, sponsoring their own movies and things like that. So a really exciting, aggressive field. And the parallelism is now over movie, which, if you like, is similar to books and documents and web pages, but somewhat larger size. But the actual processing and analysis is similar, and we've already seen possibly the most important computational type in the collaborative filtering. Here we have web search, another very familiar one. And again, I'm afraid to say this was not given to you by Google, Yahoo, or Microsoft. It was given to you by me, based again on study of the internet. In fact, this comes from the Netflix and web search use cases come from the analysis I did when I cover these applications later on in this class. So for web search, they have to return quickly enough. I don't know what it is. It used to be a tenth of a second. And a typical search only has 3 words. And you need to make certain that in the first few, when there's something called position at 10, which is how many great responses to your search are there in the first 10 ranked results. And then you need to optimize that. So if you look at what's involved in web search, it's very complicated and very difficult for new people to get into this field. You have to crawl the web to grab all this data. You have to pre-process the data to get searchable things, namely the words and positions from whatever you grab from the web. You have to form a so-called inverted index mapping the words to the documents. And when somebody comes along with a query, which is word-based, you know what documents are relevant. When you look at their query, you have to find out the documents using that inverted index, rank the relevance of the document. Here, the famous initial technique used was called PageRank from the founder of Google. But I'm sure that there are many, many methods now used, and a lot of these you will not ever hear about because they're so sensitive for the proprietary dominance or catching upness of the search world, where Google, who and Microsoft are fighting, and Baidu, etc., are fighting it out for being number one. So there's a lot of important technologies for advertising. I mean, I remember when I was around when the web, before the web started, and I remember it starting, and people were always very skeptical as how on earth anybody can make money from the web. And then somebody, I'm not certain who really did this first, realized that advertising, just as in TV, with the TV and radio had that question, initially with radio, certainly in England, where I come from, the government financed the radio as its initial business model. But then at least in the US, public radio has that feature, government and donations and things like that. However, the dominant source of media, funding for media is advertising. And then somebody had some great idea that advertising could be the model which would actually support search. And there's a huge amount of sophisticated technology to make certain exactly the right ad is put in exactly the right place, and that also that when you get results, should you get real results, and there's not, because there's lots of companies and people who will tell you how to engineer your web page to make it appear properly and within Google, and then so we not only have technology to improve our ranking, we also have technology to make certain the technology to improve our ranking doesn't work. We had Google News as an example of a page which clusters documents into topics. That's where latent and richly allocation and related technologies come in. Here we have the importance of streaming because we have to update the results efficiently. And clouds and MapReduce were probably originally first mainly produced for this particular problem. Here we notice the total size of the problem, which we actually put in an introduction to this course, 45 billion web pages total. At least that's the current estimate. This field is incredibly competitive. Mobile clients are growing very rapidly, but still they don't actually have the monetization, or whatever the word is, done quite right. Namely, there's not enough advertising on mobile clients, and so people need to work on search on mobile and how to get the mobile clients to display ads and get lots of money for those people. Another important issue is the deep web. That is the web that lies behind user interfaces to databases, where obviously the search is not so clear. And another important area of search is image search and video search, because there's more and more video and images uploaded. I mentioned in the introduction there are 500 million photos at the moment being uploaded every day, and 100 hours of video uploaded to YouTube every minute. So it's a big, big world out there. And actually, this doesn't have any striking new techniques. We already introduced them, although it should be, as I pointed out, this field actually initiated several critical of these techniques. Parallelism is over web pages, and also the parallelism is also over the users issuing the actual independent search requests. And here's another sort of big commercial application from one of the important contributors to the individuals involved in the NIST subgroup, requirement subgroup. That's disaster recovery. So disaster recovery is an important area, and clouds are wonderful for it. Namely, for example, this laptop I have here is backed up on an ongoing basis to the cloud. And since I've done that, I no longer take all these dreadful backups I used to take. And I no longer have lots of disks with lots of partial backups. But more broadly and more thoroughly, one needs to actually have a backup plan and a disaster recovery plan for enterprise data. And that has to involve people, the processes, the technology, and also the overall governance, which involves security and privacy. And we have actually replication and backup, and the data is replicated every 4 hours, at least that's the estimate here. And these data snapshots are retained for 7 days. And the complexity, and so obviously this is there are many commercial companies having entries in this field, and as far as the classification of this use case is concerned, is pleasingly parallel largely. Every file which has to be backed up can be backed up independently, so there are no important global constructs. It's pleasingly parallel, and the parallelism is not actually over the data in some senses, over the files, because nobody cares when you're doing the backup. It doesn't matter what's in your file. All that matters is there are bits there. You don't have to interpret the bits, and you don't really get data till you have interpreted bits. Here's another simple example. Well, it's not actually a simple example. It's actually a very important example. We have highlighted the Internet of Things, noting that there are going to be 75 billion things on the Internet by 2020. And one important example is just the global trucking and sending of purchases, which FedEx, UPS, and DHL do. This was sort of had a lot of recent publicity at Christmas 2013 because the bad weather actually delayed all the delivery of the growing number of purchases from internet stores. So this is pointing out that this actual process can be monitored in a much more sophisticated fashion, a more active fashion, and you could have things sprinkled on the packages, on the sites where the packages are, so that any time you can find out exactly where your package is and whether it's got lost or not. And there's a general picture on the following slide showing how trucks are monitored and go between warehouses, and they have different modes of transportation, and they have containers and pallets and other types of transportation units. And there are various standards involved here because you have lots of different people producing packages and many shippers of packages. So this particular diagram is, I think, futuristic, because although there's obviously a lot of use of sensors like RFID and things like that, it's still not probably as sophisticated as it could be. Here we have a couple of use cases, one from a data point of view and the next from a simulation point of view, covering materials. And the world is full of materials. So, because you when you manufacture something, you build it from materials. And as we go to 3D printing and everything, everybody's going to be manufacturing. We're having personalized manufacturing. So, and these materials obviously have very different properties. And as it says here, hundreds of billions of material decisions are made every year. But the actual adoption of a new material is a very time-consuming process because it is not automated and not very well supported by technology. So we can talk about the materials genome, which is sort of the idea is that the list of all materials can be electronicized and made in a much more sophisticated fashion. And also we can have repositories of materials and repositories of materials data which support discovery. The claim is the current approach is necessarily very conservative because the data is very poorly organized and very difficult to make reliable decisions. And another aspect which we'll come back to in the next use case is simulations can be important in enhancing our knowledge about materials. So in the future, the expectation is that these simulations will actually become more important. And just as we do drugs by a combination of simulation and experiment, we're going to do materials by a combination of simulation and experiment. And there have to be standards to allow the different stakeholders to talk to each other. And we need to have proper procedures, proper databases, which may or may not be SQL or NoSQL. And we need to be able to visualize these materials and make good decisions. So this is pointing out that manufacturing is going to be potentially revolutionized by building the digital material genome. So examples could be materials for making batteries, and there's a lot of effort, especially in the Department of Energy, to do massive simulations to look at the white spaces of design. And you can look at just a simulation in the aerospace industry allowed you to just go over many possible ideas for the design of a wing. Simulations in the materials world can go over many different choices for complex materials. So in here we have the actual software used. The one I know best is NWChem, which is a very large simulation developed within the Department of Energy, especially at Pacific Northwest Labs. And they actually use pretty ingenious early parallelization technology, so it's a very well-known package. And those run on supercomputers, and those produce the results which get fed into the materials genome repository. And then you're going to need to do machine learning and build knowledge systems that integrate data from publications, experiments, and simulations to support materials. Now, I note in the corresponding biology case, it's already well known the same is true, that you can get results not only from measurement, but also actually from analyzing papers, because so many papers are published, and there are too many for any one person to look at, so you can actually need to mine papers automatically, and those papers are sort of labeled by the name of the substances, and the same with materials. Those papers on materials are labeled by the things that materials are composed of, so you can actually do a very thoughtful analysis through such an analysis of existing data, surveying existing data. So we have here a new category, HPC, which is just high performance computing, and we will find other examples of that later on. This field, like the other examples, like when we do, say, astronomy, we have high-performance computing to predict the makeup of stars and how they evolve through galaxies. And we also have observation of stars and galaxies. In this case here, with materials, we have simulations of materials and data on materials coming from experimental observation. It's worth noticing that the simulations actually are also parallelized. The simulations, like in the material is a three-dimensional object. You take the space occupied by the material, divide it up into a bunch of mesh points, characterize, say, the density of the material or the polarization of the material or the particular fractional makeup in terms of its component parts, and then you do the parallelization over the mesh points with these characteristics. And we end up with a huge database of material properties, and we will also get parallelism over that database. So that's the end of the commercial applications. You notice that the last one was actually a mix of sort of research, the simulation of materials, and commercial. So that's the end of that particular lesson. Thank you very much.